Welcome to the AI on AI podcast, where we delve into the latest advancements shaping the future of artificial intelligence. Today's episode is all about bridging offline and online reinforcement learning for large language models, or LLMs. This topic intersects cutting-edge techniques and strategic implications, so whether you're a CTO or a business leader looking to harness AI, this one's for you.
Thanks for having us. Let me kick things off by framing the core challenge here. The idea of using reinforcement learning to align LLMs is not new, but transitioning between offline and online setups is like trying to rebuild the engine of a car while driving it. Offline training is stable and efficient, but it lacks adaptability, while online methods are dynamic but resource intensive.
Spot on, expert one. And when you think about it, it's a bit like the classic tortoise and hare story. Offline methods, like the tortoise, are deliberate and steady, while online methods sprint ahead with their immediacy. But the key question is, can we strike a balance, maybe a semi-online fox, if you will, that combines the best of both worlds?
I love that analogy. Before we dive deeper, let's clarify some basics for our listeners. Expert 3, as an RL specialist, can you explain what we mean by offline, online, and semi-online reinforcement learning in this context?
Absolutely, offline RL involves training a model using pre-generated data. It's efficient because you're not constantly generating new responses during training, but it's limited in its adaptability. Online RL, on the other hand, generates new data at every training step, allowing the model to learn dynamically.
Exactly. And from a business perspective, this distinction matters because the choice of approach directly impacts operational costs and timelines. Offline RL is like pre-planning a marketing campaign, lower cost, but less responsive to market changes. Online RL is like real-time programmatic advertising, powerful but expensive. Semi-online offers a hybrid, cost-effective yet reasonably adaptive.
Fascinating. Let's talk about the research findings in this area. Expert 5, as someone who has worked on RL for LLMs, what's the most surprising insight from this study?
One of the most surprising findings was that semi online methods performed almost as well as fully online methods in many scenarios. This challenges the assumption that real time data generation is the gold standard. It turns out that syncing periodically, every 10 or 100 steps, can yield comparable results while saving computational resources.
Right? And what's even more intriguing is how this plays out across different task types. For example, in verifiable tasks like math problems, semi-online and online methods both significantly outperformed offline methods. But for non-verifiable tasks like general instruction following, semi-online methods still kept pace with online setups. It's like finding that a hybrid car can match a sports car's performance in most everyday scenarios.
That's a great analogy, Expert 6, and I'd add that this finding has profound implications for scalability. Imagine training a customer service bot for a global enterprise. Fully online training might be prohibitively expensive, but semi-online methods could deliver near-optimal performance at a fraction of the cost.
I can see why this would be a game changer for businesses. But let's address the elephant in the room: stability. Online methods can be prone to instability, right? How does semi-online training mitigate this?
Great question. Stability in online RL often hinges on the frequency of model updates. By reducing the synchronization frequency, semi-online methods dampen the oscillations that can destabilize training. It's like tuning a radio. You don't need to adjust the dial constantly to get a clear signal. Periodic tweaks suffice.
And to build on that, stability isn't just a technical issue, it's a business necessity. Unstable training can lead to delayed deployments and missed opportunities. Semi online methods offer a more predictable timeline, which is critical for aligning AI investments with business objectives.
That's a critical point. Now, let's shift gears and talk about the combination of verifiable and non-verifiable tasks. Expert 5, what's the significance of training a model on both types of tasks?
It's all about generalization. Verifiable tasks, like math problems, provide clear, binary feedback, which helps fine tune the model's reasoning capabilities. Non verifiable tasks, like open ended questions, rely on reward models to estimate quality. Training on both simultaneously not only improves performance across task types, but also prevents overfitting to one kind of reward signal.
Exactly, and this dual approach is akin to cross-training in sports. A sprinter might do weightlifting to build strength and endurance, which then enhances their performance on the track. Similarly, combining task types creates a more versatile model.
Though there's a caveat here. Training on non-verifiable tasks can sometimes lead to reward hacking, where the model optimizes for superficial metrics like response length rather than quality. The study tackled this by normalizing rewards and incorporating length penalties, ensuring the model stays focused on meaningful improvements.
A nuanced approach indeed. Expert 7, from a strategic standpoint, how should enterprises think about deploying these findings?
Enterprises should view this as an opportunity to optimize both performance and ROI. For instance, a company developing an AI tutor could use verifiable tasks to ensure accuracy in subjects like math, while leveraging non-verifiable tasks for conversational fluency. By adopting semi-online methods, they can achieve this without breaking the bank.
And let's not forget the competitive edge. Companies that can efficiently fine-tune LLMs for diverse tasks will be better positioned to deliver personalized, high-quality user experiences, whether it's in customer service, education, or healthcare.
Absolutely. Before we wrap up, let's do a quick round of future predictions. What's next for RL and LLMs?
I think we'll see more focus on multitask learning, where a single model excels at a wide range of tasks. The ability to combine verifiable and non-verifiable rewards is a step in that direction.
From a technical perspective, I'd say entropy regularization will be a hot topic. It's crucial for preventing issues like response length collapse and ensuring the model remains versatile.
I agree, and as models get larger, we'll need more efficient algorithms that can leverage semi-online principles to scale training without sacrificing performance.
From a business angle, the focus will shift to real-time adaptation. Imagine an AI that can retrain itself semi-online based on live user feedback. This would be transformative for industries like e-commerce and entertainment.
Those are some exciting possibilities. Thank you all for this enlightening discussion. To our listeners, if today's episode sparked any ideas or questions, we'd love to hear from you. Until next time, stay curious and keep exploring the frontiers of AI. The research explores reinforcement learning methods for fine-tuning large language models, focusing on offline, semi-online, and online training setups. It evaluates these training paradigms for tasks with verifiable rewards, such as math problems, and non-verifiable rewards, such as instruction following. The study highlights direct preference optimization, a reward-based training method, and group reward policy optimization, which uses policy gradients to optimize rewards. Experiments reveal that offline training often underperforms compared to semi-online and online methods, which leverage updated model responses during training. Semi-online direct preference optimization achieves performance close to fully online methods while improving efficiency through asynchronous updates. Combining verifiable and non-verifiable rewards during training enhances performance across both task types, demonstrating the benefits of a mixed reward approach. The study notes challenges like response length collapse, entropy reduction, and reward hacking, emphasizing the need for stabilizing techniques and careful hyperparameter selection. Findings suggest that semi-online methods balance performance and efficiency, making them viable for complex applications requiring frequent updates. Future directions include exploring multitask scenarios, integrating additional reward types, and testing on diverse language model architectures.